Welcome to The Explainer. Today, we're unpacking some fantastic source material, specifically a complete experimental detailed video on the determination of dissolved oxygen in water, presented by Dr. Chem. We're looking at one of the most vital, yet literally invisible indicators of water quality on the planet, dissolved oxygen, or just DO for short. Whether you're managing a sprawling wastewater treatment facility, monitoring a fragile coastal ecosystem, or honestly just running a home aquarium, understanding DO is absolutely essential. Okay, let's dive into this and uncover the science behind how we actually measure the breadth of our waterways.
Here is our quick roadmap for today. Section 1 is understanding dissolved oxygen. Section 2, factors controlling oxygen levels. Section 3, the classic Winkler titration. Section 4, modern dissolved oxygen sensors. And we'll wrap up with Section 5, calibration and best practices. So we're going to start with natural ecology, transition right into hardcore laboratory chemistry, and finally explore the modern electronic engineering that lets us track these levels in real time.
All right, Section 1, Understanding Dissolved Oxygen. To kick things off, let's look at the foundational concept itself, because it poses a seemingly counterintuitive idea. I mean, how exactly do you find a breathable gas hidden entirely inside a liquid?
Well, it's a super common misconception that dissolved oxygen refers to the oxygen atom already bonded to the hydrogen within the water molecule itself. Actually, scratch that, that is not the case at all. The DO we're talking about is free-floating, pure oxygen gas, O2, that literally dissolves and fits seamlessly into the microscopic spaces between individual H2O molecules. Think of it exactly like sugar or salt dissolving into a glass of water. This free-floating gas is what aquatic organisms, from microscopic bacteria to giant game fish, are actually breathing through their gills.
When we measure this dissolved gas, we typically use milligrams per liter. And, the magic number we're often looking for is right around 8 to 9 milligrams per liter. This specific concentration indicates a really high-quality water condition. At this level, natural ecosystems are absolutely thriving, aquatic life is fully supported, and if we're talking about an industrial context, it indicates an excellent, highly sanitized wastewater treatment output.
But here's the thing. Water can't just hold an infinite amount of oxygen. And that brings us to Section 2, Factors Controlling Oxygen Levels. Let's look at the environmental elements that actually dictate how much oxygen a water system can physically hold at any given time.
Now, what's really interesting here is how these three specific variables work together to place a strict cap on the natural oxygen saturation level. It's a very delicate balancing act. As water temperature rises, its ability to hold oxygen drops. When atmospheric pressure drops, say you're up at a really high altitude, DO levels also decrease. And finally, salinity plays a huge role. Saltier ocean water holds way less oxygen than fresh river water. Combined, these three factors define the absolute maximum amount of oxygen your specific water system can hold.
So, we know what dissolved oxygen is, and we know why it fluctuates. But how do we actually measure an invisible gas trapped in the liquid? That brings us to Section 3. The classic Winkler titration. Let's transition from the what and why to the how, and look at the foundational chemistry of oxygen measurement.
Way before the era of digital sensors, there was the Winkler titration. This highly precise chemical method was originally developed all the way back in 1888, which is incredible history. And, honestly, over a century later, it remarkably remains a gold standard. In fact, it is still the preferred method for assaying precise oceanic levels of oxygen in uncontaminated seawater. It relies entirely on chemical reactions rather than electronic signals.
This is where that experimental, detailed video presented by Dr. Chem really shines, showing us this exact lab-style walkthrough. First, you carefully collect your water in a specialized glass flask without trapping a single air bubble. Then you fix the oxygen by adding manganese chloride and an alkali. This reacts with the invisible DO to form a highly visible, brown, cloudy precipitate. Next, you drop the pH by adding sulfuric acid. This dissolves that brown cloud and releases free iodine into the liquid, turning the whole thing a deep yellow. Finally, you slowly titrate that yellow solution with standard sodium thiosulfate, literally drop by drop, until it turns completely clear. The amount of thiosulfate it takes to make the liquid clear tells you exactly how much oxygen was originally in the water. It's a beautiful, color-changing visual cue that makes complex chemistry feel as approachable as following a cooking recipe.
But there is a massive catch when you're doing this manually. As the Massachusetts Institute of Technology Laboratory Manual stresses in all caps, Do not allow the sample to sit for any length of time. The sample must be run immediately. This strict authoritative directive really emphasizes just how volatile dissolved oxygen is. If you let a stagnant sample just sit open to the air, atmospheric oxygen will instantly begin diffusing into your liquid, completely ruining the accuracy of your reading.
Which naturally leads us to ask the million-dollar question. Is there a faster, less chemically intensive way to measure DO out in the field without hauling around a heavy crate of fragile glass bottles and corrosive acids?
Thankfully, yes. Welcome to Section 4, Modern Dissolved Oxygen Sensors. We have officially entered the era of advanced electronic instruments that have completely revolutionized environmental monitoring and continuous wastewater treatment operations.
You can think of this like a data quality management method menu recognized by environmental agencies. We just discussed the Titration method, coded DO, using those special glass bottles to avoid air contact. Then there's the colorimetric method, which uses small vacuum ampules with preloaded chemicals for quick visual checks. But the real game changer for field and remote monitoring is that third row right there. The polarographic or optical electronic sensors, coded DO, which measure oxygen flux directly.
And this brilliantly illustrates that depending on the device you choose off that menu, the underlying scientific principles shift dramatically. We are moving entirely away from manually neutralizing chemicals in a flask, and instead we're relying on sophisticated physical and electrical signals interpreted by tiny microprocessors.
Let's see how this builds into two competing modern technologies, optical and polographic sensors. Directly contrasting these two, it's wild to see they solve the exact same problem in entirely different ways. The optical, or fluorescence method on the left, uses light. It shines a blue light onto a special material, causing it to glow red. Oxygen molecules naturally quench or dampen that red light. By timing exactly how fast the red light fades, the sensor calculates the oxygen level. Now on the right, the polographic method uses a direct electrochemical reaction. Dissolved oxygen passes through a membrane and literally steals electrons from a gold electrode, creating a tiny but measurable electrical current.
So the crucial point here is that whether you're using high-tech lasers or gold electrodes, these instruments are incredibly sensitive. And that brings us to our final stop, Section 5, Calibration and Best Practices. Knowing how to actually operate and maintain these tools is the only way you're going to get accurate, defensible data.
Before you ever head out into the field or drop a sensor into a treatment tank, you have to calibrate it. There are two primary ways to do this. First is zero-point calibration. Here, you use a chemical oxygen scavenger, like sodium sulfite, to strip literally all the oxygen out of a water sample, artificially creating a true zero baseline for your sensor. The second method is air-saturated calibration. For this one, you suspend the sensor in 100% water vapor, so it's not submerged, but sitting in a highly humid air environment. The sensor's computer uses the current ambient temperature and barometric pressure to calculate exactly what the 100% theoretical saturation should be, locking in its upper limit.
But listen, even with a perfectly calibrated sensor, operators frequently make crucial mistakes that completely ruin their data. These are the top pitfalls to avoid. Never neglect your regular baseline calibrations. Always ensure your temperature compensation features are active. Remember, temperature dictates oxygen capacity. If you're using a polarographic sensor, you absolutely must actively stir the sample. Because the electrode physically consumes oxygen as it reads it, stagnant water will quickly give you a false low reading. Also, never use outdated or expired sensor membranes, and be incredibly careful not to trap atmospheric air bubbles near the sensor when you're prepping your sample.
By combining those classical chemistry principles we saw with Dr. Chem with strict modern technological discipline, we can accurately track the invisible lifeline of our waterways. So, I'll leave you with this final provocative thought. How much hidden oxygen is currently sustaining the ecosystem in the nearest body of water to you right now? And what would happen to that environment or that industrial process if it suddenly plummeted? Understanding and measuring DO gives us the power to answer those exact questions before it's too late. Thanks for joining me on this explainer. Keep questioning and keep learning.